Hey science students, Leslie here from Tesla Tuition Videos. And today we are doing the physics topic of Newton's first law of motion. Okay, let's check it out. Okay, so today we are conquering Newton's first law of motion. And before we read the definition, it should be noted that Newton's first law is very much related to forces in equilibrium, because for all objects in Newton's first law, those objects are essentially in equilibrium, meaning that all the forces acting on those objects are balanced, so the net or resultant force is equal to zero. So it's safe to say that all equilibrium questions are essentially also Newton's first law questions, and that's why it's so important for you to have seen my lesson on forces in equilibrium, because the same techniques that were dealt with there will be also used for Newton's first law calculations. Okay, now what about the definition of Newton's first law? Well, for grade 11 learners doing both the government school or CAPS curriculum and the private school or IEB curriculum, as well as grade 12s doing the IEB private school curriculum, the definitions are virtually identical. And the definition reads as follows. An object continues in a state of rest or uniform, moving with constant velocity, unless it is acted upon by an unbalanced net or resultant force. Now, for our grade 12 learners doing the government school or CAPS curriculum, there is a slightly different but very similar wording of the definition as described by the latest exam guidelines for our grade 12s in the government schools. Now, we'll put that definition up on the screen now, but that definition, that wording of the definition for our government grade 12s, it reads as follows. A body will remain in its state of rest or motion at a constant velocity unless a non-zero resultant or net force acts upon it. Okay, very similar definition. So what are these definitions really saying to us? Well, what they're saying is that in order for an object to not be moving at a constant velocity or to stop being stationary, a net or resultant force or unbalanced force needs to act on it. But for an object to remain at rest or moving at a constant velocity, there is no net or resultant force that needs to be acting on it. And that means that for Newton's first law, all objects, also known as bodies, will have balanced forces acting on it and no net or resultant force. So all forces will be balanced for objects that are at rest or moving at a constant velocity. Also, remember the word uniform means constant or unchanging. Okay, so now that we've looked at the definitions for Newton's first law, let's take a closer look at some of the concepts that it involves. Okay, so moving on, Newton's first law deals with objects that are either remaining stationary or at rest, in other words, not moving, or they are moving with a constant speed or velocity that isn't changing. And they will tell you what type of motion the object has in the question. This means that there is no acceleration of your object, because in order to have acceleration, your velocity or speed needs to change over time. So if it doesn't, if velocity stays the same or constant, then there is no acceleration of the object. And that's the theme of Newton's first law. It's all about objects that have zero acceleration. And this means that they will have a zero net or resultant force acting on the object, meaning that all forces acting on the object, both parallel and perpendicular to the surface, are balanced. And this ultimately means that forces going in one direction are equal in magnitude or amount to forces going in the opposite direction. Right, and this is the idea that you will use to solve for unknowns in Newton's first law calculations. Okay, let's move on. Okay, so under Newton's first law is the concept of inertia. Now, the definition of inertia is only required of our private school learners doing the IEB syllabus, but our government school learners doing the CAP syllabus, even though they might not be asked to define inertia, they still need to understand how it works and be able to apply it to certain examples. So the definition kind of explains what it is as well. So for our private school learners, the definition of inertia is that it is the property of an object that causes it to resist a change in its state of rest or uniform motion. Now, what that means is that an object's inertia causes it to want to obey Newton's first law. In other words, if the object was at rest when some kind of change happens, its inertia will want it to keep at rest. Now, if an object is moving at a constant velocity when some kind of change occurs, then according to the object's inertia, it will try and maintain or keep its constant velocity that it was moving at originally. Also, in my own words, I can say that inertia sort of tells us that when a change is made to an object's surroundings, the object will try and maintain or keep its original motion that it had before the change was made, even if that means continuing to be at rest. Now, inertia can have some pretty interesting effects that you might have to explain in a theory question, and I'm going to go through a couple of them now, and then we'll do a big example that they want you to know about in your curriculum guidelines. We'll come back to that example, which involves the importance of wearing seatbelts, but I'm first just going to talk through a couple other examples. Okay, so consider maybe a lady that is walking with a bucket of water balanced on her head, and maybe the lady is walking at a constant velocity. All of a sudden, the lady sees a snake in her path, causing her to stop abruptly. So the lady has stopped moving, and that's the change. But the bucket of water, which is not physically connected to her head, the bucket of water will experience inertia. And after the lady has stopped suddenly, the bucket of water will continue moving forward at the original constant velocity that the lady had before she stopped. And that means after the lady has stopped, the bucket of water with its inertia continues moving forward, and it will literally fall forwards off her head. So another example would be getting the last of the tomato sauce out of a bottle by shaking a bottle like we do to get the last of the sauce out of the bottle. Now, the sauce is not physically connected to the bottle, so when you move the bottle down and then suddenly stop your hand, the tomato sauce at the back of the bottle will experience inertia and continue moving forward at the original velocity that your hand was moving at before your hand stopped. So once the bottle has stopped, the tomato sauce continues moving forward towards the neck of the bottle, the front of the bottle, where we can now more easily get it out of the bottle. So yes, inertia also helps to get the last of the sauce out of a bottle. Now let's take a look at another example. Right, so the specific example of inertia that learners are required to understand and be able to explain in a question has got to do with the importance of wearing a seatbelt, which obviously has to do with safety. So let's talk about what happens to a passenger who is not wearing a seatbelt. And we've written the example down here. So imagine that a car is driving at a constant velocity, and the passenger next to the driver is not wearing their seatbelt. Now, let's assume the driver is wearing their seatbelt, but the passenger is not. Now, the car might suddenly come to a stop, maybe because it sees a stop sign suddenly, and you'll see that the passenger of the car is going to carry on moving forward. Now, what's going on here? Well, the passenger is not wearing a seatbelt, and if they were, the seatbelt would exert a net or resultant force on the passenger that would allow them to slow down with the car. But without a seatbelt exerting that net force to slow down the passenger's body is now going to experience inertia. So the car is braking, and the passenger's body that's experiencing inertia will continue moving forward at the original velocity the car was moving at before the car stopped. And that means that the passenger's body continues moving forward after the car has stopped, and so the passenger will likely crash into the windscreen. So by wearing a seatbelt, you'll see that the seatbelt actually physically connects the passenger to the car, and it will exert an unbalanced or net or resultant force on a passenger while the car is braking to bring the passenger to a stop with the car. But without that seatbelt, without that net or resultant force, the passenger's body experiencing inertia continues moving forward because it's trying to maintain its original velocity before the car stopped. So that's inertia for you. And please be able to explain certain stories or scenarios with regards to inertia in a test or exam question. Okay. That brings us to the end of today's lesson on Newton's first law of motion. Head over to our website for our full-length science videos.